Soumya, are you available?
Yes, sir.
Shivam Saab, are you there?
Yes, sir.
Then we can start. Soumya, we can start.
Okay, sir. Now we move forward to our next technical session on demonstration of EV fast charger MATLAB for V2G and G2V. It is my pleasure to welcome once again our speaker for this session, Mr. Shivam Srivastav, sir. Sir, the virtual stage is all yours.
Thank you.
ये सब बड़बड़ाया करते हैं।
प्लीज अनम्यूट कर दीजिए अपना माइक।
Hopefully my screen is visible to all.
Just a minute. Shivam Saab, let me unmute. Okay, I think Shivam Saab, from your side the voice is coming. Fine, your
Yes,
screen
yes.
is visible.
Okay. So in this session, we are going to just have a look or the demonstration of the EV fast charger for V2G and the G2V conversion, G2V stage. So for this, we are having a pre-built model in our library section. Okay. Now coming back to this, we have a automation tab. In this automotive tab, the very first example by the name of a electric vehicle. So this particular example you can just see on the screen right now. It is an example related to the electric vehicle with fast charger, which is representing for the both the condition of the charger, that is for the vehicle to grid and the grid to vehicle. So in this scenario, you are able to see that we are having a three subsystems. Okay, so the very first subsystem is by the name of a grid and the residential load. The second subsystem is by the name of a charging station, and the third subsystem is by the name of a electric vehicle. Okay, so in this complete EV system, we are having one induction motor which is having a rating of a 270 kilowatt, while we are also having a lithium ion battery which is having a capacity of 250 ampere hour. Now, for the charging scenario, or we are having a battery charger of 175 kilovolt ampere, which is implemented for by using the battery inverter component, which you can just easily simply drag and drop to the from the library section. This particularly the battery inverter component being used for the battery charger is supporting for the grid forming and the grid following mode. If we just give a little bit idea about the grid forming mode, it is means that when the inverter is going to act as a voltage source known as a grid forming mode, while when for the grid following mode, the inverter will act as a current source. So the again we are having a operation for the charging station that could be go for the vehicle to grid to vehicle, and the UPS operation, that is simply charging the battery or the UPS we are having at our the residential area or at the charging station area. The powertrain module or the powertrain control for the electric vehicle that we are using is for the field oriented for with the regenerative braking concept. The regenerative braking concept is means whenever the braking is applied, the battery is going to be charged. The model is has a load which is being connected at the residential area is having a capacity of a 20 kilovolt ampere, which is simulating the UPS mode, and it is done by the switching the battery inverter from the to the grid forming mode and the disconnecting the uh, our the grid. So let's just we are in this scenario, you can just see that we are having a three tabs are available, that is by the name of a open model, which is letting you to open the model or the open access to the model, which is directly taking us to the schematic editor, where we can just simply open each and every component of this particular example model. We are having a application node which is giving you the complete detailed description about how this model has been created, what type of the subsystem they have been used, what are the different components they have used, and what are the different type of the equations that is being used for generating or for building this kind of the electric vehicle V2G G2V concept. Again, the open test, which is a Python based script, has been already prepared for this example, which is giving you the idea how many number of the tests are going to be performed. And on after running those test script, we are generating a report in the Euler format, which could be in the HTML format or it could be in the PDF format depending upon the user requirement. The report is giving you the full-fledged idea about how many number of the tests are going to pass and how many number of the tests are going to be failed. So let's just begin with this opening the application node, where we can have a look of the this particular documentation, which will be giving you the detailed description or the idea about how this model has been, some little bit of introduction. After this, it is giving you the idea about each and every subsystem that is been already described by the name of a grid and the residential load, charging station, and the electric vehicle. Then the each and every subsystem has been again elaborated how this grid and residential subsystem has been created. It is consisting of a one three-phase voltage source. Again, the measurement terminal for the grid is, or the grid impedance has been implemented. Then a contactor for connecting or disconnecting the residential load to the system. After this, we are also having an electric vehicle which is consisting of a three main components, which is having a lithium-ion battery, three-phase inverter with LC filter, and the induction motor. So this is the battery inverter. You can simply drag and drop from the library section. You need not to just develop this kind of the thing by your own. Though you are having a leverage to parameterize each and every component inside the subsystem also, or you can just simply just assign the values, what should be the nominal power, voltage, and the DC link voltage for this battery inverter parameter. So this particular table is giving you the idea about the of the parameters associated with the battery inverter. So starting with the nominal power, nominal voltage, nominal DC link voltage, what it should be the default value and what are there the new values. Again, when we are talking about, we are having a battery inside our model, so they must be having a parameters like a nominal voltage and their capacity for the lithium ion battery. So they are, this particular table is giving you the idea about how the things are associated with this particular battery parameters. Again, we this particular EV model is having a various kind of the signal processing components, which is the, you can just see that these are the some of the mathematical equations or the C function code or the logical operator or for the relational operator that could be used, or the some PID controller or the PWM generators, these kind of the things. So we are having a very big model that could be, we are going to see. Again, this is a subsystem that will be associated with the electric vehicle. We can just zoom inside this particular image. So if I just open the image in the new tab, so you can just see this is our image related to this our electric vehicle subsystem, which is you can just see this is having a contactor which is going to be connected with the vehicle charging station logic. This is a this particularly the powertrain control module for controlling the this our electric motor. and these are the measurement terminal for measuring the various type of the parameters being associated with this uh, induction motor or the inverter parameters we are having. Again, we are having an induction machine, and the mechanical model has been created for controlling the various type of the load and the what are the outputs we are generating from the electric machine. Okay, after this, the once we are focusing on the charging station, there must be some specific idea that what could be the possibilities to be keep in mind once we are connecting the our vehicle with a charging station. That means the vehicle should be in the stationary position, it should not be in the running condition when we are connecting the it to the charging station, and when it should not be disconnected to the charging station while during the charging. Only the vehicle not be in running position while in the charging condition, and and it is also to prevent the motor from the starting when it is connected to the charger. So there are the some possible scenarios that we should implement inside the C function block that is going to be control these such scenarios, and which is going to be helpful for your what we can say the preventing the electric vehicle and also preventing our charging station for some severe damage. After this, we are having some powertrain control module which we are having. So it will be giving you the idea what type of the control module we are having. So this particular module is implementing the whatever the flux calculation or the reference flux we are having. Then we are focusing on the id current, iq current, and their reference speed, and on the basis of that we are having a svpwm reference generator where we are generating a various kind of the mechanical sorry pwm signal for the different legs of the for the different legs of the inverter we are having, that is by the name of a MA, MB, and NC. Again, we can just go for the what are the parameters we could mention about the electrical motor, that we are focusing on what should be its nominal voltage, power, frequency, and the maximum RPM, and the number of the pairs we could go for. So after this, you can just see that torque reference equation should be have. So in this particularly giving you the some C function block having some logic that is being to limiting the acceleration power and the acceleration torque, regenerative braking power, regenerative braking torque, and the some multiples for the throttle or the percentage scenarios. After this, it is giving you the idea about what type of the different kinds of the mathematical equations that is being directly associated with the our electric vehicle, whether they are in the what type of the different load or the forces are being applied, that is the mechanical force or the braking force or the force due to the load. What happened if we are applying the for the load that is being for the gradient resistance or the rolling resistance or the wind resistance that you have already analyzed in the previous session, that is related to the electric vehicle simulation due to the with the help of the signal processing components in the previous sessions. So these are the various kind of the equations has been already used. After this, it is giving you the idea what type of the SCADA panel will be looking like. So the SCADA panel is also a quite huge. So it is giving you the complete leverage of what could be the dashboard will be looking like, how the charging station should be look like, what are the different operations should we have. So we can go for the whether it should be the charging condition for, or it should be the vehicle to grid, or it should be the UPS mode, or or its charger should be disconnected. So these are the different status that could be captured inside the different scenarios, and where we can just follow the what could be the mode, whether it should be the grid following mode or the grid forming mode. And we can also observe the various kind of the parameters for the DC fast charging, what should be the terminal voltage, frequency, DC link, battery charger, various type of the curves, and the digital displays, and the LEDs, and again we are having a leverage to just increase or decrease the reference frequency, voltage, and the power, and the active power and the reactive power depend by using the slider options. So again, we can also go for the various type of the capturing the different type of the voltages and the current related to the armature. We can also go for the capturing the results related to the power and the torque. What happened if we are limiting the throttle value, or we are just going for the this is increasing the speed beyond the limit, or decreasing the instantaneously we are applying the brake. So these kind of the certain scenarios we can go for, and we can just observe those kind of the result also. Now in the test, it is this particular example is also having a test automation. So the documentation is also giving you the idea about the what should be the test automation report will be look like, and what are the number of the tests are going to be performed. So it is giving you the idea about the what should be the response of this particular electric vehicle under the different kinds of the throttle values, when the acceleration is 30%, 50%, 80%, or the 100%. So these kind of the different scenarios we are going to observe, and it will be giving you the this kind of the Euler report, and it is assigning you the complete detailed description along with the various curves and the data that has been collected while after running the different types of the test. So this particular test, as you can see on the screen, I can just open the image in the another tab, so you can just see this particular report is giving you the idea that the this example is having a 5 number of the test, out of which the 3 have been failed and 2 only have been passed. So this particular logic that they have created for creating a for this type of the test scenarios in the Python environment. So this test scenarios in the Typhoon test IDE can be should be in the Python environment, so that if the user is not very much confident with the Python scripting, so they can also take a help from the API that is being created by the Typhoon team. So inside the APIs, they need to just give the name of the signal on which they want to just perform the test, and the value of this particular thing, so at which they want to perform the test. Like the if they are performed to go for the performing on the acceleration test for on the speeds related to the acceleration of the electric vehicle, and the value should be the 30% or 40% or the 60%. So these kind of the things they can just implement inside the Typhoon test ID. Again, coming back to the documentation, so this is giving you the complete curves along in this, so where it is giving you the what should be the curves related to the torque and the power. So these are the things we are getting with this pre-certification report. Again, this is at the last the minimum requirement of this example that could have once if you are going to run this model while using a physical agile device with you. So the it is consisting of a how many number of the device should be you have, how which model you should have, what should be the configuration, what are the number of the processing cores, what should be the maximum matrix memory utilization, maximum time slot utilization, simulation time step, and the execution rate of the signal processing component. So these are the little bit information about the device and the detailed description about the complete example, whether it should be the schematic editor or it should be the SCADA panel, has been elaboratedly described right over in this Typhoon Hill documentation tab. So after discussing the detailed description, we can just open the model by simply clicking on the open model tab, and the model will be automatically open on the schematic editor section. So once we are can see the model is right over there, so you can just observe that we are having this model, and you can just see this all are the subsystems. So once I will just double click, so it will be indicating that this is a subsystem that include a grid and this information related to the subsystem, but we are not able to open it. Similarly for the charging station, and similarly for the electric vehicle, but I want to just see what is inside this. So what we need to do is right click on this, and you can just see at the bottom there is a mask. Go to mask, then go to look under the mask. So inside this look under the marks, so we are having a subsystem of the grid and the residential load. So this kind of this thing we have already seen in the documentation, where you can just see that we are having this particular value of this voltage that we are applying as a source voltage of the or the grid voltage, which is having a 240 divided by np dot sqrt 3. So this np is indicating the calling the numpy library for from the Python environment. After this, we are having a grid impedance. So that is defines as a RL grid impedance, which is having a nominal line-to-line voltage, short circuit power, inductive power factor, nominal frequency, all are mentioned over here. Then we are having a uh, sing, three poles, three poles single throw contactor. After this, we are having a residential load, which is also having a which is also a subsystem that has been created and having a nominal power frequency, voltage and the power factor. If you want to go inside it, so you can again right click, go to mask and look under the mask, and you can just see this residential load is nothing else. It is a combination of a RL component is connected in parallel. Okay, so this kind of the things we are having with the our grid and the residential load. Now coming back to this charging station, so you can just see the difference that the grid residential block is in black color while the charging station is in the blue color. But the connection between the grid residential and the charging station is with the black color, sorry. So the reason behind is this, the if I just again go back to this inside the subsystem of the grid and the residential, all the component are in the black color. That means these black color components are going to run on the FPGA of our HL device, and the ports that is by the name of the 1 2 3 are available are going to be the electrical port, not a signal processing port of our device. So this could be done like this. So after once coming back to the charging station, now go to mask, look under the mask. Now you can see that we are having a battery inverter which is in the blue color, while the connection of the battery inverter ABC terminal at this the left side, while the DC POC POS and the DC NEG, these are on the right side, are, are in black color. This battery inverter component you can need not to just design yourself, you can simply drag and drop this particular component from the library itself. The reason of the core coupling that we are using right over here is that the in the previous sessions you have already discussed about the things like that each of the HL devices consisting of the core, and while the you have also discussed about this particular device table also. So if I just give you the quick review about this device configuration table. So the this particular example is working on the Hill 506, which is having the configuration number of the one, which has been selected right over here. And you can just see that our first configuration is having a four cores has been allocated for the signal processing core, while the one core is allocated for the machine solver. So what is happening right over here? So once what happened if we are having a four cores for the electric machine, so that to be need to be separated by some sort of the thing, so that the each component should be have a clear cut idea in which core they have to go for, because each and every core is having a weightage of a maximum up to the 3. So if any of the component is using a inverter, three-phase inverter or the three-phase rectifier, which is also having a maximum weightage of the 3, so beyond this, the if the core is having a weight of the 6 or some more than 3, so it will be giving you the error. So on the base to remove those error, we are using this core coupling. So the reason so again if I just double click on this, So before double clicking, if I just go to mask and the look under the mask, you can just see that we are having a one three-phase inverter. If I double click on this, it is having a weight of the three. So this complete pack of the charging station, which is consisting of a battery inverter, is going to occupy the one complete core of the FPGA that we are going to use. So before this and after this, that is the before the core coupling 1 and after the core coupling 2, these things to be moved to the different cores, rather than the battery inverter should have the separate core. So now again, coming back to this, if I double click, so in the general tab you can just see the parameters that could be allocated with this battery inverter, like the nominal power, voltage, DC link voltage, nominal frequency, switching frequency, and the execution rate. You can go for the filter components, you can go for the advanced component, which is consisting of a PLL datas, or the say voltage and the frequencies related to the KP and the KI values, and the phase difference that could be accepted with the synchronization with the KP and the KI values. Again, we are having a advanced mode 2 for the current parameters related to the ID IQ, which is associated with the KP and KI for the PI controller. Again, for the voltage mode, and for the again for the modulation signal for the upper limit, lower limit, and the other factors. So again, if I just go to mask and the look under the mask, you can just see this is the pre-packed thing. So this thing is consisting of a inverter, some sort of the passive component, that is the RLC components, and some of the converter measurement units we are having. Then we are having some current measurements. Then we are having a once again switch that which is going to be controlled by some of the feedbacks from the controlling signal that we have created, which is going to be control the contactor stage. And again, we are having some grid measurement terminal. Again, we are using some of the controller for this controlling this battery inverter, which is consisting, if I just little bit zoom it, so you can just have a detailed view over it. So you can just see that we are having a inverter capabilities. We have V mode control, we have the charging control mode, duty cycle. You can just observe those duty cycle, how to just maintain that. You can just go for the ABC to DQ mode, power measurement, synchronization. Again, you can, if I just double click on this every, so these all are also a subsystem for another things. So this is a very huge block that we are bringing from the library section, that is a battery inverter. Though it is consisting of a three-phase inverter, that's why it is getting a weightage of the three, as the every component that we are seeing right over here are majorly in the blue in color, that is going to be run on the CPU of the HL device, while the passive component are not going to that much space inside the FPGA of the HL device. After this, you can just see that there must be some output and the input for this battery inverter. So they are having a one more subsystem that is having a simply the output, and the this particularly the input. So this is also subsystem. Then look under the mask, and which is having a various type of the SCADA inputs for turning on it, what type of it should be the mode, what should be the frequency, reference frequency, reference voltage, active power reference, passive power reference, so reactive power reference. So these kind of the things we are controlling. So we can just observe what should be the values they have been assigned for the SCADA input, what should be the what are the parameters they have been allocated for the charging station and all. So these kind of the thing they have been used. After this, coming back to this electric vehicle component, so we can again go to mask and the look under the mask, and again you can just see this component is again having a three-phase inverter and a induction machine. Okay, so now the induction machine is having a separate core. That's why we have selected the 506 configuration number 1, so which is having a one separate core allocated for this machine, while the 4 cores are allocated for the power electronic component, that is the three-phase inverter or the rectifier. So that's why we have separated the things. Again, we are having a one control logic for this vehicle charging and the running logic, whether they are should be the running or it should be the charging. So these are the control logic we have created. So they have created for checking the whether the vehicle is has been stopped or not. If it is stopped, so it will be checking for the closing the contactor, vehicle is in off mode, and the contactor is blocked by the charger. Again, if it is blocked by the opening, the if the charger is opened, okay, it is that means indicating that the motor has been started, something like that. This kind of the logic they have created. Okay, so after this, for this PCM, that is a powertrain control module, they have been created a IFOC controller. So or the logic they have been created, so where they have been focusing on the what type of the reference flux or the flux calculation, then they are calculating the ID regulator and then IQ regulator. On the basis of that, they are generating the some sort of the PWM signal that is going to be just control the switching of the our switches of the inverter. So you can just double click on this each and every block, so you can just see this all are the C function blocks. So you can just see what should be the output, input, what are the various variable parameters, and what should be the what are the different code they have been written over here. So you can just observe those kind of the things and try to understand what logic they have been created. Again, they are also focusing on the theta calculation, how the theta has to be calculated. Then the one more block, that is by the name of the integrator rollover, how this block has been created. So you, if you have facing any difficulty with any block, so you can just double click, go to help section and go to the documentation hub, where you can just easily simply find the each and every detailed description about the component. So these kind of the things we are having. Again, we are having a one block by the name of a three-phase power meter, where we are just measuring the what should be the measurement we need to go for different uh, possibilities we are having from the grid or the three-phase system, like a power, voltage and frequency, voltage RMS or the current RMS. So you can just select what are the things you want to go for. So simply by selecting those things, we can just set these kind of things. After this, we are getting an output, and we are having a n number of the or the 5 6 outputs from this simple three-phase meter, and you want to just separate those kind of the things. So we are using a meter split. So this is a block where we are just selecting what are the outputs we are getting out from this three-phase meter, and where we are connecting whether the probe or the some go to from block, where we are just sending those signal from one place to the another place. After this, where we are just have a consumption calculator, where we are calculating the consumption of energy, how much energy the vehicle has been consumed for covering a certain distance. After this, they are having some mechanical model, where they are just focusing on the braking of the braking force, and whether the for the regenerative braking purpose, and where they are just calculating the speed for which they have some subsystem over there based on this particular equation. And then also they are having a load force calculator, where they are just calculating this force of the load that is being associated with the gradient force, loading rolling force, and the wind force, which is also the being made by this equation that has been mentioned in this yellow color comment box. So you can just simply double click on this, and you can just observe those kind of the things, what should be the uh, equations they are using, and how those equations they has been implemented inside the typhoon environment. So these kind of the things they can be done. Okay, so again, we are having a electrical machine and the three-phase inverter, where we can just simply double click, and you can just observe we are having a three-phase inverter which has been currently set into the internal modulator. After selecting the electric three-phase inverter in the internal modulator, you can just see the four tabs are available by the name of the enable, INA, INB, and INC. So enable is indicating for enabling the inverter to turn on and turn off, while INA, INB, and INC are for accepting the PWM signals for different lags of phase A, B, and C of the inverter. Again, we are also having an option for the digital input per switch, where we can just give the digital signals to the per switch basis from the HL device inside the software also, where if we have originally generated some sort of the PWM signal outside the Hill device. Again, we can go for the per lag also, where we can just select the dead time period, where which is also for the when the no, for the purpose of the node 2 switches must can be cannot be operated at the same time. So for this reason we can just go for that also. Again, we can go for the model section, where the thing is going to change like that, where when the your complete carrier signal and the reference signal are going to be implemented inside the typhoon environment only, and you generating the PWM signal inside the typhoon environment only. So these kind of the scenarios you can just perform on the basis of this. You can just controlling your inverter, where you can also go for the measurement, you can go for the enable the delay, you can go for the losses calculation, you can go for the comparator studies, you can go for the everything, whatever the possibilities for the with this particular induction, oh sorry, inverter. After this we are having an induction machine, so where you can just go for the what type of the model. You can go for the linear machine or the non-linear machine, where you can assign the parameters. You can go for the what are the mechanical parameters, what should be the load, whether it should be the torque, SCADA externally, you or the externally controlling thing, or the modeling controlling your thing, what type of the model you are going to, or the load you are working on, whether it should be the speed type or the torque type, what should be the feedback, what should be the snubber value, what are the output you are going to obtain, and what are the fault you want to just apply on this electric vehicle, or the sorry, the electrical machine. So these are the things you can just perform over this. Now coming back to the route, we can just have a look what the huge model has been created by the typhoon. So it is not easy to just build those kind of the model inside within a week also, because it's need a quite a very big calculations that to be made inside that, so each and every block can be implemented, and how, or because each and everything is related to the other part of the component, and which is need a very big things to be calculated. So we can just simply run this model, because I am running in this kind of the model within the virtual mode, because I am not having a 506 with me currently. So I'm running this model in the virtual hill mode. So you can, if you are having your system with you, so you can just also run this model on the virtual hill mode, and you can just observe the results at your end also. So before going to the SCADA panel, let's just discuss more about the what is we are getting in this inside this thing that is over here. Okay, so let's discuss this kind of the thing also. So this is the thing, or the output that we are getting, or the compilation output that we are getting once we have clicked on the compile and load the model in the hill SCADA, which is going to we can observe. And on by due to this observation we can get a much more idea what the things we have implemented, or what are the things we have run or the compiled inside the model. Okay, so the very first line is it is indicating no device detected. Okay, that means currently hill device is not detected, so the model is going to be load in the virtual hill mode. After this, this in the green color, it is indicating the validation is passed. That is indicating that whatever the connections that we have made are correct. That means there is no open port is available inside it. So the thing is that we are have whatever the connections we have made, it is correct. Again, whatever the values we have assigned are feasible, or the feasible means that means are not going to create that much severity with our hill device. So this kind of the things we are getting with this validation pass. After this hill 0, it is indicating that the what if the device it is nothing else than device id, because at the back end of the every hill device there is the ids are present, so you can just select over this. After this we are having a device configuration by the name of the hill 506 in the configuration number 1, where we have the four codes has been allocated for the our this uh, power electronic components. So on the basis of that, it is indicating that the SPC0, it has these kind of the component, that is the battery inverter converter measurement, and the battery inverter converter measurement for VA. So these simply we can say the battery inverter is for the SPC1, SPC0. Then again, another is having the induction motor, and third one is having the residential load section. So these are the things we are having. After this we are having some sort of the communication lines has been completed. That means that whatever the connections has been created between the each subsystem has been completed. After this we can just go for running each and every component. So that means indicating the standard processing core utilization. That means we are having the 4 cores, and out of which we have run the for the 3, and we for the machine server we have 1, and we have completed for the 1. DC-DC converter, we don't have any DC-DC converter inside this. What type of the signal generator utilization, what are the lookup table utilization, PWM modulator utilization, analyzer utilization, TTV connectors utilization. So these all are the things we can just observe over there. After this, how many converter models we have in each of the codes, we can also look for that also, and how many space they are going to just take inside our HL device is that is also mentioned over here. After this they can go starting with the say, calculating the things in the signal processing component, where they are just observing the simulation time step, scale discrete setup step to this particular value, this kind of the thing. Then they are going for the what it's the matrix memory utilization of the core 1 2 and 0, and for the time slot utilization of the 0 1 2 core, and for what type of the losses this calculation, machine dynamic model calculation, or for or due to all this, these all the electrical part has been complied successfully. After this we are moving for the how many the signal processing SCADA component, output component, input component has been used. These all are the what are the C function code has been we have used. So these all are the things we have compiled successfully. So this message has been we have used. Again, you have observed in the very beginning that we are having something in a orange color also, that have been discussed with you. Okay, so this this is indicating a warning that the both the code data and the data section, both the code section and the data section will be put into the external memory. So if the error is or the warning is coming into the orange color, that could be ignored, because if this kind of the error has been eliminated while we are using the actual hill device with our system, once it is connected with the system. Okay, if the error is in the red color, that need to be rectified. Okay, so these are the things that to be discussed before moving towards the hill device or the SCADA panel. So again, it is asking us to the unable to connect the hardware device, load the model to the virtual hill, because I haven't connected the system, my system with the actual hill device. So let's just wait for a few seconds so that the SCADA panel will open to you. So now just click on the pre-existing file by the name of a electric vehicle .cus. So I'm just clicking on this, and then you can just observe the things. let me just set the screen. Okay. So this kind of the SCADA panel is already developed by the Typhoon team, and we need to just simply run this model and we can just observe the things. So currently you can just see that this SCADA panel is consisting of subsystems or the groups. So the very first group is by the name of a electric vehicle, which is nothing as the dashboard of the electric vehicle, which is giving you the idea about the speed or the speed related curve and the battery is parameters for or the battery status. Again, the this picture of the vehicle from the downward side is indicating the display or the things like the whether the battery is fetching the giving the power to the inverter or not. These kind of the things is happening over here. After this we are having a one sub group by the name of the operation mode preset, where the it is indicating the EV charging this mode, that is a uh, grid to vehicle, then vehicle to grid, and then UPS system. Again, we are having a fast charging station, which is nothing else again a subsystem, which is consisting of various types of the uh, gauges, which is consisting of a terminal voltage, frequency, DC link voltage, battery charge, and the various type of the digital display curves and the LEDs and the slider options, where we can just change the values of the voltage reference, frequency reference, active power reference, and the reactive power reference. Again, we are having a status symbol for what type of the status of this particular vehicle or the mode of the charging we are having, whether they are connected to the grid or at a standby or vehicle to grid or grid to vehicle or the UPS mode. After this we are having this capture scope widget, which is nothing as a inbuilt oscilloscope of our Typhoon environment. So let's begin with this running the model. So currently at the bottom you can just see that it is mentioned that a virtual hill mode, because we are not connected with the actual hill device, we are running the model in the virtual hill mode. So let me just click on this green color play button present at the bottom side. So after clicking on this, we are ready to run this model. After running the model, there is an also button on the dashboard, that is to start and stop the electric vehicle. So I'm just clicking on the start button. Then slowly I will just increase the speed reference to a certain value. Let's suggest for a 80. Okay. So as soon as I have just set the speed reference and vehicle has been started, so you can just observe the LED beside this macro widget has been blown. Again, the curve associated to this particular speed reference has been start to increase. Also, the torque and the motor RPM has also started. Since how much distance the electric vehicle has been covered is also coming on this text display. It is also mentioning the electric torque, average consumption of the energy is available. Again, we are also able to see the battery SOC. Before starting the vehicle, the battery SOC was 80%, but after starting the vehicle, the battery SOC has been started decreasing rapidly. Okay. Now we are having a torque and the power related graphs also inside this tab. So if we just click on this, so we can just observe the torque versus speed and the power versus speed curves right inside this torque power graphs. So you can just observe this, and these are also continuously increasing or the moving to capture the result. So let's just wait for a few seconds so that we can just see that how much this vehicle is moving, or how much it is coming to the particular speed scenarios. After that, we will just move towards the regenerative braking as section, and that's kind of the things. So let's just, I will just start decreasing the speed, and I will just increase the brake at a full, and I will just reduce the speed. So once I have just pushed the brake to the 100% and speed has been reduced to 0, so you can just observe that this green LED related to the regenerative braking has been glown, and you can also observe now the battery SoC will start to charge due to the regenerative braking. Again, you can also see that the electrical torque has been decreased, speed is also going to reduce, and consumption energy is also going to be reduced. So you can just see the previously the battery SoC was at 79.55, now it is showing the 79.57. We can also observe the curves related to the torque versus speed and the power versus speed like this after applying the regenerative braking. Now, once the speed reaches to 0, we can just remove the brakes, stop the vehicle, and coming back to the panel route. One more thing we can just see, okay, then we can just have a look for the another things. So we can just start with the EV charging. Now we can just see that the vehicle it was at a charging of 79.57, something like that. So we can just start with the vehicle charging. Let's just connect with the charging mode. Click on this EV charging. Okay, now it is charging. You can just observe that the grid to vehicle, the arrow is indicating that charging station to the battery, and you can also observe after a few seconds the battery SoC will going to be start from 79.57. It is already reached to the 79.60. Once it is fully charged, we will just coming back to this section that what is known as a standby, and again for the vehicle to grid, and then for the UPS section. Again, by the time you can also observe the whatever the related curves we are having for the electric vehicle three-phase meter A, B, and C, for the VAN, VB, and VCN for the currents, voltages, and the mechanical torque, electrical torque, and the battery current. We can also observe these kind of the things. Now we can see that the battery SoC is start increasing, and and soon it will reach to the 80%, and once it will be reached to the 80%, it may be disconnected to the charger, because the capacity of the battery has been capped at to the 80% only. In a few seconds it is going to be 80%. So SCADA panel is not so a tough thing to be visualize the thing, but though it is a quite simple thing, but we need to just understand the how to just relate the things that we have built in the schematic editor, and how it could be related with the what are the widgets we are taking inside the SCADA panel, and how we can just observe the things over the SCADA panel, and similarly how to control the things and how to just verify the results we are getting inside the SCADA panel. So it is approximately 80%, that is 79.97. In a few seconds only it will be just 80%. Okay, so now it is reached to the 80%, so we can just go for the grid to vehicle mode.
सर मीटिंग में है जी जी बताइए.
Once we
हाँ
have
हाँ
just,
वोट ऑफ थैंक्स आप ही देंगे और स्पेशल.
once we have clicked to the vehicle to grid mode,
नहीं
so
नहीं 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 सर, असल बात एफडीपी का वो जो वैलिडिटी कराना ना, फीडबैक वाला मैं करा दूंगा, क्योंकि उसमें हर को बुलाना थोड़ा आपको दिक्कत होगी सर उसमें. हाँ बस. जी 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 जी. और अर्चना अर्चना मैडम के बाद आप वोट ऑफ थैंक्स करेंगे सर. आए जी जी. ओके सर. जी सर.
so after this section, the EV charging, once we have charged the battery, we can just click on the vehicle to grid mode, and where we can just observe now the battery is the charge of the battery is going to be uh, moved towards the vehicle to the grid, and which is being indicated by the red color arrows, and the red color LED has been blown, which is indicating that the vehicle to grid mode. Again, you can also observe that the value related to the battery SOC is being going to be decreased. That is for the starting from the 80%, it is now reducing towards the 79. Again, we can also connect to the simple UPS. That means we are now connecting to the simply the battery that we are having at our charging station. So now you can just see it is only the one LED is going to be connected, or the glowing, that is for the UPS, which is in the red color, while the very first LED which was till now is glowing, that is for the connected to the grid. Now it's turned off. Now the again the battery charge is moving from the battery towards the UPS section, so the red color arrow is coming from the battery towards the DC fast charger. Again, we can also observe that the battery which current is going to be increasing rapidly, which is indicating that we are just having the value that is the charging the battery. Again, if we have the limited the thing, we now want to just disconnect this charging, so we can just click on the disconnect the charging. So if once we have disconnected the charging, the UPS charging will be stopped. So you can just see that the whatever the LEDs was glowing previously was now stopped, and this is being indicated by the dotted lines. So this could be the done with this particular schematic editor and the SCADA panel related to the electric vehicle V2G G2V example model. So we can just do this kind of the things. So I can just see that we are having a few more minutes left. So I can just give you the quick review about the one more example related to the thermal losses. So the in the thermal losses that is also related to our the vehicle section, because whatever the model we are moving making must be having a some sort of the losses inside it. Okay, so whether we are talking about the motor or whether we are talking about the inverter or the rectifier, we are having some kind of the things we are having, the losses must be there. So these losses must be calculated. So this is the particular examples related to the losses section, where you can just see after double click. This is a simple three-phase inverter, you must be knowing now. Okay, so there is a very last tab by the name of a losses section. So if you just click on this losses calculation, you are having an option to import the XML file related to the switches and related to the diode directly from the manufacturer website. So you can just whatever the inverter or the rectifier you are going to use in the physical environment, so you must be having a knowledge what should be the switches they are being used or they are being using, or simply you can just see if you are making a inverter by your own. So you must be having a clear cut idea what type of the inverter you are going to make and what type of the switches you are going to implement inside this. And for the switches you must be aware of what from what manufacturing unit you are taking or purchasing those kind of the things. So from their website you are bringing the XML file inside the environment, and you are having a leverage to select the what type of the switch, whether they are IGBT or the MOSFET. Depending upon the type of the switch, you can just bring those files, and after bringing those files, all the data from the XML file will be automatically updated right over here. Okay, so you need not to enter those kind of the things by your own. Again, if you are going for the temperature calculation for also after the losses calculation, so you can just select what type of the temperature thermal network you are going to perform, whether it should be a Foster type or the coil type, and depending upon those kind of the things, complete data has been imported from the XML sheet to the this particular thing. Similarly, you can just make a for this kind of the thing for the for rectifier also. You can all, if you don't have a file with you, you can import the data by your own by simply typing the data inside the different tabs are available for the voltages, currents, and temperature on the this losses tab. Again, if you are working for the motor losses calculation, you can just simply double click on this, come into this output section in the advanced okay, just a second. In this motor section, we can just go for the, okay, we are having our losses in this particular, we are having a thermal model we have created, and where we are just creating this thermal network by using this particular component by the name of a thermal network only, where we are focusing what type of the network we are using, whether the capacitor or the coil, and depending upon those kind of the things, we have just taking the output, and we have just created a C function block where we are having a some sort of the C functions related to the resistance of the motor we are going to have inside our model. Again, similarly for the heat sink thermal model, we are having this kind of the different cases, temperature and the power losses we are having. And again, we can go for the similarly for the rectifier. Again, you can go for the thinking that how the efficiency of this model has been calculated. So you can have a leverage to calculate the efficiency of from the what is the input power, rectifier loss, inverter loss, stator loss, mechanical loss of the motor. And depending upon all the scenarios, you can just develop a C function code, and beside of this, on the basis of that, you can just calculate the overall efficiency of your system. So you can just see, have a look over there. So we are having a this kind of the function for the this our efficiency section of this model. So I just quickly run this model, and you can just simply observe the what type of the SCADA panel they have created. will take few seconds only. So till the time, is anyone having a doubt related to the previous example, like electric vehicle example that we have seen right now? So if you have installed the software at your end, so you can have a full access to each and every example that we are having. So you can just go through those examples at your end and learn more and more about the typhoon environment and how those could be implemented at your place. So this is a complete network, or the complete SCADA panel has been developed for the this thermal losses calculation. I'll just quickly just run this model, and you can just see there are also a different tabs are available, and you can just see that starting from the grid section, where the voltage, grid mode, LVRT pulses, and the phase voltages VAB, VBC, and VCA, and the DC link bus voltage, and the braking status, and the ambient temperature, friction coefficient, speed reference, constant load value, what should be the machine speed, machine current that we are taking out from the taking inside the machine, motor temperature, rectifier losses, and the inverter losses, stator losses, mechanical losses, overall efficiency, input power, all the things we can just observe. Again, if I just double click on this, and you can just observe the waveforms related to the currents that we are the instantaneous current is starting from the source side, and the DC voltages, grid measurement, grid voltages, and the machine mechanical speed. Again, you can just observe the data related to the rectifier, their cases, temperature, and the power losses. Similarly, for the inverter, we can just observe the cases, temperature for the upper junction switches and upper switches, and the bottom switches, power losses for the upper switches and the bottom switches. And similarly for the machine parameters, where you can just observe the machine losses, motor temperature, and the stator resistances. So you can just also change the from the balance to the unbalance, and now you can just also observe the what is the impact will be appearing on side your waveforms and data as you are having under this kind of the things you can just observe in the unbalanced condition, these kind of the waveform we are getting. Again, we can just also observe the this disruption inside this rectifier losses calculation, inverter losses calculation, this disruption you can just observe in the power loss, and similarly for the machines. So we can just stop till this part only. So we can just stop here, and can just coming back to this main screen and just close this SCADA panel and schematic editor. You can also go through this application note, where the complete detailed description is mentioned about this model, what is happening inside the model, and what are the details about the different data related to the how the bringing the files and how to build the model, and what should be the SCADA output. We can just observe everything has been mentioned right over here, and and also mentioning the minimum requirement of this particular example model. So you can just go through those kind of the things. So at this point, I'm just stop sharing my screen. And if anyone is having a doubt related to this two examples that we have seen in today's session, that is related to the demonstration of the EV fast chargers for the V2G and the G2V, and also for the thermal losses calculation, you can just ask.
Sonali Basu, She is having any doubt, I think. She has written in the chat box. Yes, Sonali, please ask.
Yeah,
Sir, I would like to ask what is the correlation between this battery simulation and the actual vehicle conditions, sir?
okay, the course simulation or the relation you are asking about?
Yes,
The
sir.
uh,
Between this battery simulation and the actual vehicle.
Okay, so the thing is that whenever we are going for the simulation results, so the thing is we are not going for the offline simulation. We are working on the real-time simulation. So when we talk about the real-time simulation, that means you are running all the things in the real-time scenarios. Once we have connected the actual hill device with our system, everything is shifted from the virtual environment to the real environment, and now they are going to be taking the realistic data. That means you, whatever the equipment or whatever the motor, inverter, battery you are going to be used in the physical environment, those physical data you are using those data inside your software environment as a input data parameters, and now you are just validating those results and observing what happened if the you are going to implement such kind of things in the physical world. So before going to the physical implementation, you are testing the results into the our agile system. And one more thing that you are asking about, the one word, that is a course simulation. So the course simulation is a different word in our domain. So the course simulation is means that we are the Typhoon Hill is the product that is being majorly focusing on the electrical parameters or the electrical simulation. We haven't focused on the mechanical simulation. That means we are not focusing on the mechanical turbulence inside the vehicle or the road disturbance or the road conditions, such kind of things. So for this, we are having a different tools by the name of the IPG car maker or something like that. So we are having the core simulation with that. So whatever the electrical parameter you can just develop inside the Typhoon Hill environment, and what are the mechanical parameters you can just develop inside the IPG car maker, and you can just have a core simulate those things. That means in one system Typhoon Hill, in one another system you are having a IPG car maker, and connecting both the system, and you are observing the result of both the things at the same time.
Okay, sir. Thank you. Sir, I would like to ask one more thing, sir. DC battery basically charging the DC battery takes 30 minutes, sir. Let's take an example that it takes 30 minutes. So in this simulation, will it be 30 minutes or it will take more time?
Once we have connected, if we haven't connected the system with a HL, it will take more time. Okay, but if we have connecting the HL device with our system, then it will going to be take approximate 30 minutes or the 30 to 35 minutes only, because the whatever the result we are getting from the Typhoon Hill or the HL device, it is correctly up to the 95 to 98% correct results.
Thank you, sir.
Thank you.
Thank you so much, Mr. Shivam Shrivastava sir, for such a wonderful and insightful session. Your explanation and practical perspectives have truly enhanced our understanding of the topic. On behalf of the organizing team and all the participants, I extend our sincere gratitude to you. Now, as we move towards the conclusion of today's program, we shall proceed with the valedictory function. I welcome convener and coordinator in
Beta,
Charlie Cell and
Soumya,
next commissioner.
Soumya,
Yes,
we will stop here for 2 minutes. Then we will start because we have to come on air, right? So screen has to be changed. So this meeting, dear participant, this meeting is going to stop for just for 2 minutes. Then again we will reassemble for valedictory session. Thank you. Calculate the attendance.